Hi, and welcome back to Techmar's Advanced Heat Pump Control Training for Radiant Heating and Cooling. This is the third module in our course, and this module is going to focus on heat pump system design considerations. So the first module that we covered together focused on the overview of radiant heating and cooling. The second module included an overview of heat pumps, and now we're going to look at the factors that we need to consider for a well-designed, high-performance geothermal system. All of the parts of the system have to be properly designed and controlled. They're all sort of like cogs in the wheel. From a control perspective, the entire system needs to be well designed for the control to operate as intended and as expected. In fact, to design the mechanical system with a control solution in mind is what we recommend. Otherwise, you may be faced with having the extra expense of a customized control solution to fit your mechanical design. So we'll look at the outline that we're going to cover today. The outline for today's module is to look at the components of a ground source heat pump system. Then we'll focus in on the geothermal system design, and that will include the loop, or the ground heat exchanger, the heat pump itself, and the buffer tank. Lastly, we'll look at the control and distribution design, and that will include distribution system options. So what type of terminal unit should we be looking at for a geothermal system? And then we'll start to look at some of the control features that Techmar has created to optimize the system, and that will include outdoor temperature reset, indoor temperature feedback, and zone synchronization. So each of those items will give you a better controlled system and will increase the operating efficiency of the geothermal system. The three main components of a heat pump system are the ground source. So this is going to include the ground heat exchanger. And what is that design? Then we're going to look at the heat pump and control. And this area includes the equipment in the mechanical room. So this is also where we're going to be talking about the buffer tank. And lastly, we have our distribution system. So this is where we're looking at the types of terminal units and the type of distribution design that is best suited for a geothermal system. Now, as I said, each of those three components is essential to get right, and the best way is to design all three of those pieces at the same time. There's nothing worse than designing part of your system and then being stuck or limited in your options for the other components. They're all pieces of the puzzle, and we have to make sure that they're all working together and complement each other. So the efficiency and the reliability of the geothermal heat pump system depend on how well each of the components work together. So we're relying on the sizing and the design of the ground heat exchanger. If the earth loop isn't sized appropriately, then we're going to have a lot of trouble with the rest of the system. So that's the first thing that we need to focus our attention on and make sure that it is sized appropriately. That leads us into the sizing of the heat pump. So we'll look at how we need to size the heat pump to match what we've done with the ground heat exchanger and to match what we need on the load side of the building. Next, we'll look at the selection and sizing of the distribution system. It's not just the selection of the terminal units, it's how they need to be sized in order to work well with the low supply water temperature. And the last piece of the puzzle is, of course, where our expertise comes in, and that is the system control. And when I talk about control, I'm also going to be steering you towards zone control as well. So not just the system control, but also the zone controls and how those two can work together in order to optimize the geothermal system. So we saw this chart in the previous module. I'm just going to bring it to your attention again. We know that the efficiency of the heat pump is optimized when we have the lowest possible entering load water temperatures and the highest possible entering source water temperature. Now this is for heating only. We're talking about coefficient of performance, which is directly related to the heating cycle of the heat pump. So if the lower my entering load water temperature, so the lower the temperature of the water that's being distributed to my terminal units, I can see this translates into the highest coefficient of performance or COP ratings. Likewise, the warmer my entering source water temperature, so the warmer the water coming in from my ground heat exchanger, the higher my COP will be as well. So we actually want the smallest temperature difference between my entering source water temperature and my entering load water temperature. So remember, even if you have the best control solution, if we are not working with the optimal entering load water temperature and the optimal entering source water temperature, then the controls will not be able to impact the efficiency the way they were designed to do. We're going to begin by looking at the ground source design. In particular, how do we keep that entering source water temperature as high as possible in heating mode and as low as possible in cooling mode? That's a big piece of the efficiency puzzle, is to get that entering source water temperature where it needs to be so that we don't have to do as much temperature lift. A ground loop, or a ground heat exchanger, consists of a loop of pipe containing a circulated fluid. If we're talking about an open loop, then that fluid is water. If we're talking about a closed loop, then the fluid would be a glycol solution. And that circulating fluid is pumped around the loop to collect and transfer energy. So an open loop system pumps water from a well, pond, or lake through the heat exchanger and then discharges it back to the ground. It's the least expensive to install and has very high efficiencies. However, you have to have an ample water source, and there are inevitable concerns about water quality. So we have to take a look at what types of impurities might be in the water, if there are minerals, what are the quantities of minerals and particles, is there organic matter that we need to worry about? All those can damage the heat pump system. You also have to worry about potential licensing requirements depending on where you live and what jurisdiction you're in, as an improperly installed system can have a considerable environmental impact. We're going to be focusing on the closed loop system. The closed loop system presents no environmental impact to the earth or aquifers, so no special licensing is required. And there are a variety of different closed loop designs, and we'll take a look at 3 of those designs in the coming slides. It is critical to design the earth loop properly because the efficiency and the capacity of this system depends on our entering water temperature. So the first thing we need to do is to determine the building's accurate heating and cooling loads. We want to stay away from those general rule of thumb equations and do a more detailed and thorough analysis that will give us an accurate load. Next, we're going to select a horizontal or a vertical loop design, and we'll look at the selection criteria for choosing one or the other in the coming slides. Once we have decided if we're doing a horizontal or vertical loop, we can use the building's heating and cooling loads to size the ground loop heat exchanger accordingly. First, we'll look at the horizontal loop design. So with this design method, the loops are installed horizontally. And this is done when there is adequate yard space to do so. So the key word there is adequate yard space. It is only an option if you have the land space. So it's great for rural properties with large land areas. But otherwise, if you don't have the land space, then this will not be the ground heat exchanger design that you select. The spacing is approximately 10 feet apart, and we bury these tubes at a depth of 4 to 8 feet below the ground surface. So because we're not going too far below the ground surface, we do have variation in soil conditions. So the deeper we can dig within the ground, then the more stable those earth temperatures are going to be. But because we are not going too far with the horizontal loop, we might have some variation with the seasons. The plus side of the horizontal loop is it does have a lower installation cost. So ground heat exchangers are very expensive. It typically represents about 30 to 50% of the total system cost. So it's if we can reduce those installation costs with the horizontal loop design, it can make a big difference on the overall price tag of the geothermal system. The rule of thumb for a horizontal loop sizing is up to 150 feet per ton of heat pump capacity. The next loop design we're going to look at is the Slinky loop, and that's actually what we have installed here at Techmar. So the picture you see there is taken from our own installation. That Slinky loop is buried under our parking lot, believe it or not. The Slinky loop is similar to the horizontal loop, but because we are overlapping, we require less land space. So we're reducing the heat exchanger per foot requirement, but increasing our pipe requirement. And because pipe is cheaper than digging, we still are ahead of the game as far as cost is concerned. And the rule of thumb for the Slinky loop sizing is 600 to 800 feet or more of pipe in 125 to 150 foot trench per ton of heat pump output. The vertical loop heat exchanger design is probably the design that we see most often, and one of the reasons why is because it has the lowest land area requirement. So the locations that we can use this ground heat exchanger design are more prevalent than with the horizontal design. The boreholes that we drill down into the earth can be up to 300 feet deep. And the plus side to that is that we have stable soil temperatures. Since we are going so far deep into the earth, we are not susceptible to seasonal changes in the earth temperature. So that's a big advantage to the vertical loop design. The biggest drawback to the vertical loop design is that it is the most expensive installation. And that is because it requires drilling as opposed to trenching. And with the drilling, we need to hire experienced vertical loop installers, not conventional oil drillers, but loop installers, and the equipment that we need is more expensive as well. So for those reasons, this is the most expensive design, but we also have the greatest capacity with this design. Now, we talked about these different ground heat exchanger designs, but what are the factors that we need to consider for sizing these loops? So what factors do we need to consider for loop sizing? Well, sizing is based on the building loads, the soil conditions, and the local climate. And it's very important to get the sizing of the ground heat exchanger right. If it's sized too large, we're going to have unnecessarily high costs. And remember, the ground heat exchanger installation represents 30 to 50% of the total system cost, so we don't want to be spending more money here than we need to. If it's sized too small, we're going to have failures. So undersizing can result in that ground loop running colder and colder, and at worst can result in the ground temperatures not being able to recover. So if we're extracting heat from the ground at a faster rate than it's being recharged, then we have an unsustainable process. So we want to make sure that we size our ground loop heat exchanger appropriately. It must be sized according to the building loads and to deliver energy at no greater rate than the surrounding earth can collect energy over a 12-month period. Now we'll look at how we can design for soil conditions on the following slide. So the factors that are going to affect the loop sizing from a ground condition point of view are the soil temperature, the soil moisture level, the density of the soil, the depth of the tubing below the surface, the tube spacing, how far apart are we spacing our tubes, and the diameter of the tubes. So to have a decrease in loop size, what we're going to see are higher soil temperatures, wetter soil, higher density soil, deeper tubing, wider tube spacing, and larger diameter tubing. So all of those factors will decrease the size of our ground heat exchanger loop. On the flip side, if we have lower soil temperatures, or if we have dry soils or lower density soils, we're going to need to increase the size of our ground heat exchanger loop. Likewise, if the depth of tubing is shallow, if the tubes are spaced close together, and if we're using small diameter tubing, all of those will also increase the size that we need for our ground loop heat exchanger. So it's important to take all of these factors into consideration when we are sizing that geoloop. It's essential that the heat pump and the ground heat exchanger are designed together. So the design and selection of each of these components depends on the other. The sizing of the loop is based on the capacity of the heat pump, and the efficiency of the heat pump is a function of the water temperature produced by the ground loop. Now, those typical entering water temperatures can have a lot of range. As we've just discussed, it depends on the location of the installation, the ground heat exchanger configuration, the soil or rock type, and the economics of the installation. All of these factors place practical limits on the highest entering water temperature that we can design for. And that has to be considered carefully when we are selecting the appropriate heat pump. Now, when it comes to heat pump sizing, it may be economic to size the heat pump system to meet only a portion of the design load. Now, we're going to look at this in greater detail in the last module of this course. But backup or auxiliary heating can be used to supplement the heating capacity. So a general rule of thumb is that the heat pump is sized to meet 60 to 70% of the design heating load. And in doing so, it actually meets most of the annual heating energy requirements. Now, the reason we don't want to size it to meet 100% of the load is an economic factor. So the larger we size our heat pump for, that means the larger we have to design our ground loop heat exchanger. And the ground loop heat exchanger is, as we've said a couple times now, 30 to 50% of the total system cost. So it may not be in our economic best interests to size that ground heat exchanger and the heat pump to meet 100% of the load. Because really, the only times we need 100% is at peak demand, and peak demand typically happens maybe only 1% of the year. So those are the reasons we would consider downsizing to meet only 60 to 70% of the design load, and then using backup or auxiliary heating to make up the extra capacity during peak demand. Now, the size of the buffer tank should be determined based on the predominant use of the heat pump. So is the heat pump going to be in heating or cooling mode for most of the year? For us in Canada, it's definitely predominantly used for heating. Same with the northern United States. But if you're in the southern United States, you're probably using that heat pump for cooling most of the time. So your buffer tank would be sized for your cooling load in that case. Now, the reason it's so important to size that buffer tank appropriately is to prevent equipment short cycling. It also allows us to have different flow rates through the heat pump than through the distribution side. So we get that hydraulic separation with the use of the buffer tank. Now, the heat pump usually needs a much higher water flow rate than the hydronic load, so operating without a buffer tank can cause refrigeration circuit problems. So we can avoid all of that by including the buffer tank, and that will save our heat pump from cycling on and off, and it will give us the hydraulic separation that we need. Now, how do we size the buffer tank? It's actually pretty straightforward to size. We have the formula written on this slide right here. So it's based on 4 variables. The first one is the duration of the heating or cooling source on time. So this is this small t here. Now typically we're looking at 5 or 10 minutes for heat pumps. The second variable is the minimum rate of heat input. So here we have our Q heat source, and that is the minimum rate of heat input. So that's going to be our BTU per hour. The third variable is the minimum system load. So this is our small q, load. That's our minimum system load, also in BTU per hour. And that is going to be divided by the allowable tank temperature. So what is the temperature rise of the tank from when the heat source is turned on to when it's turned off? So those are our four variables. We have, again, the time that the heat pump is on for, typically 5 to 10 minutes. We have the minimum rate of heat input into the system minus the minimum system load divided by the allowable tank temperature rise from when the heat pump is turned on to when it's turned off, multiplied by a factor of 500. So very straightforward to size that buffer tank appropriately, and it's important to do so to make sure your system is operating as efficiently as possible. So now that we've looked at our overall system from the point of view of the ground source loop, the heat pump, and the buffer tank, we're going to look at the control and the distribution side of things. Now we know that the key to efficiency is to keep the entering source water temperature and the entering load temperature as close as possible. Now the entering source water temperature has to do with the ground source, but the entering load water temperature has a lot to do with our application design and our distribution system design. So we'll look at that on the following slides. Anything we can do to reduce the water temperature in the distribution system is going to increase the capacity and the efficiency of our heat pump. So here we have another graph where on the left-hand side we can see the heat pump capacity, and that's in thousands of BTU per hour. On the bottom axis we have our entering source water temperature, ESWT. And we're showing three different entering load water temperatures, 100 Fahrenheit, 115 Fahrenheit, and all the way up to 130 Fahrenheit. You can see that we get the highest capacity when our entering load water temperature is at its lowest. So here at 100 degrees Fahrenheit, the capacity of our heat pump is by far the highest. And also when our entering source water temperature is at its highest. So we want the high entering source water temperature and the low entering load water temperature to give us that maximum heat pump capacity and efficiency. What that means is we have to design the distribution system for low supply water temperatures. Now, we typically recommend that design temperatures should not exceed 120. And that's for the R410 refrigerant, which by far most heat pumps utilize. If you have a different type of heat pump that's using another refrigerant that allows for higher design temperatures, then that would be something else. But typically, we want to make sure that our design temperatures do not exceed 120 degrees Fahrenheit. So that means we need to select the appropriate terminal units. This is a chart that shows us the suggested range for a variety of terminal units. So on the low end, we have our high mass slab. So that would be the slab on grade. And you can see we can operate this with very low water temperatures. We're looking at 90 degrees Fahrenheit up to 110 degrees Fahrenheit. So that would be ideal for a geothermal heat pump system. Next we have a low mass slab, so that would be a thin slab installation. And here we have a range in temperatures of 100 up to about 125, so again this works well with the geothermal system. And we can also use low temperature radiators and low temperature baseboard. These can both be utilized with low supply water temperatures. So we have a range here of 100 to about 140. We'd want to keep that on the low side, so between 100 and 120. What we're not going to be using are traditional radiators, traditional fan coils, and traditional baseboard. All of these require supply water temperatures that are just too high for a geothermal heat pump application. Now, where does the control come into play? Well, we know that efficiency is maximized when we operate the heat distribution system at the lowest possible temperature. And part of that has to do with the selection of the terminal units. But another part of that comes through control. So what can we do to reduce that temperature as much as possible without impacting occupant comfort? We're going to look at 3 different control features. And the first 2 we'll look at are outdoor temperature reset and indoor temperature feedback, and how both of these features act to lower supply temperatures wherever possible. So outdoor temperature reset is a term that probably most of you have heard of in terms of boilers. So virtually all boiler controls now have the outdoor temperature reset feature, and we're going to look at how it can apply to an optimized geothermal heat pump system. First, we'll go over the traditional operation, and then look at how an outdoor reset control can make a positive impact on the efficiency of the geothermal heat pump system. So traditionally, our heat pump would always be operated to provide the design entering load water temperature. So let's say we've designed our distribution system so that the design temperature is 120 degrees Fahrenheit. Traditionally, we would just be maintaining our buffer tank at 120 degrees Fahrenheit. So if you look at the screen, we have a cold night. Let's say this is a cold winter's night, and our buffer tank is being kept at 120 degrees Fahrenheit by our heat pump, and we can see the heat into our space is equal to the heat out of our space. However, on a sunny day, we're not going to need our distribution system to be operating with 120 degrees Fahrenheit. But our heat pump is still being operated to maintain that buffer tank at 120. So we're going to be cycling that heat pump on and off to maintain a buffer tank temperature of 120 degrees when we don't need supply water temperatures that are that high. So what's the impact of this? Well, we're going to see temperature swings. Our system is going to be operating at high water temperatures for a short period of time to satisfy the thermostat before it turns off again. So we're going to see an overshoot, and then we're going to suddenly turn that system off until we drop below set point, so we're going to see that undershoot. It's an inefficient use of energy. We're going to have the on-off cycling of our heat pump and the equipment. And because we're delivering that high water temperature when we don't need to be, we're going to experience expansion noises. The solution is an outdoor temperature reset control. So this is where we're going to vary the entering load temperature based on the current outdoor temperature. So in a heat pump system, that means we're adjusting the tank target based on the estimated heat loss or the outdoor temperature. And doing so will result in significant savings and improved comfort. So the blue line here is what we call our outdoor reset curve. And you can see this outdoor reset curve varies according to outdoor temperature. So when we have extremely low outdoor temperatures, that's when we're going to see our design temperature at 120. However, as the outdoor temperature increases, we don't need that 120 water. We're going to see our entering load water temperature, or our tank target, decrease as the outdoor temperature increases. So instead of maintaining 120 degrees regardless of outdoor temperature, regardless of the heat loss the building will experience, we're going to vary based on the estimated heat loss from our building. So here's how it works. When the thermostat calls for heat, the control is going to operate the heat pump to supply an outdoor reset temperature. So the outdoor reset control uses an outdoor sensor to measure the outdoor temperature. And the goal here is to match the building's heat loss with the heat supply. So we look at that outdoor temperature, determine what the estimated heat loss is for the building, and deliver an appropriate amount of heat. So here we have 3 of our heat arrows being delivered to the space and 3 heat arrows leaving. So we have a balanced heat delivery and heat loss. On colder days, we're going to have greater heat loss, so we need greater heat supply. So our outdoor reset control is looking at the outdoor temperature, sees that it's colder outside, knows that we are going to have greater heat loss from our building, and so we need to adjust the tank target accordingly for a greater heat supply. Now, on warmer days, our outdoor reset control is going to adjust the tank target for a lower entering load water temperature. So in this case, it's a hot sunny day. We're going to lower our tank target and deliver minimal heat into the space that matches the heat loss from the building. Energy is saved every time the tank target is below the design temperature. So this in green is my savings range. When I'm using outdoor temperature reset and I'm varying my tank target based on outdoor temperature, anytime I'm below 120, that is energy savings. Of course, not only is it just energy savings, but when we have a heat pump application, it's going to increase the efficiency of the heat pump by lowering those entering load water temperatures whenever possible. So outdoor temperature reset is a great start. Now we're going to look at some additional control features which will allow us to even further reduce that entering load water temperature. We do that through communication. Communicating controls allow us to assess the actual needs of each individual zone and coordinate the functions within the overall system. And the implications for that are fine-tuning target temperatures based on need, coordinating cycles, and for heat-cool switchover. So this is a very important consideration for a geothermal system design. How do we know it's time to switch the system from heating to cooling and vice versa? How do we present zones from trying to heat while the tank is filled with chilled water? These are all considerations that are addressed with communication. So over the next few slides, we're going to focus on how communication will help us to further reduce system water temperatures and further prevent equipment short cycling. Starting with indoor temperature feedback. Now, a lot of you have probably heard of indoor temperature feedback as it relates to our boiler controls, and the same theory applies to our heat pump controls and our zone controls. We can use the communication from the zone control to the system control to further reduce that entering load water temperature whenever possible. And the reason this is significant is because environmental changes cause significant variation in the required heat input. So not all spaces can be treated equally. We can see from the image we have here, perhaps there's one room that, because of where it's located, is typically a lot cooler than the other rooms. And perhaps we have a room over here that experiences a lot of solar gain, so it is much warmer than the other rooms. These are all factors that we have to take into consideration to optimize our system and not treat every single zone as if it were the same. So let's take a look at how outdoor temperature reset certainly helps us, but doesn't go all the way. So if we look in red, this would be my reset curve. Now my reset curve works really well for the month of November, but it's not working so well for this shoulder season, September, October, and it's even supplying more heat than I need in December and January. What that means is my tank target is higher than it needs to be for most of the heating season. and my heat pump is likely cycling on and off to maintain a higher target temperature than is necessary. I'm having temperature swings in my zones, and I'm wasting energy and not seeing high efficiencies from my heat pump when I could. As a reminder, the coefficient of performance from my heat pump is optimized when my entering load water temperature is at its lowest. So the fact that in the previous slide my tank target was higher than it needed to be for a lot of the year meant that I'm compromising the coefficient of performance. I'm compromising the efficiency of my heat pump. So what can I do about it? The solution is indoor temperature feedback. Now this is only possible because of communication between the zones and the system control. So what is shown on the slide right now is a heat loss chart for various months of the year. The red curve is the reset curve based on outdoor temperature reset. And you can see this works perfectly well for the month of September. However, in October, the heat loss from my building is much lower, which means I need a lower heat supply to compensate for that loss. If I'm operating strictly based on my outdoor reset curve, my supply water temperatures are going to be much higher than they need to be. What indoor temperature feedback does is it will decrease the supply temperatures by shifting the heat curve down based on the input from the zones, so that my reset curve is shifted down so my heat supply more readily matches the heat loss. Now if I go into the month of November, I can see I'm experiencing a higher heat loss than the reset curve had predicted. So I need a higher supply water temperature to make up for the increased loss. Indoor temperature feedback will shift the heat curve up so that I have higher supply temperatures than what was originally calculated. And so the automatic shifting of the reset curve depending on feedback from the zones is what allows us to have more fine-tuning of our system. It allows us to reduce our supply water temperatures wherever we can, but still provide the comfort that occupants demand. We are not compromising on comfort, we're actually increasing comfort because we're matching the heat delivery to the actual heat loss of the space. So indoor temperature feedback will automatically lower the tank target temperature in response to solar or occupant caused heat gains. So let's look here at the chart we have on the slide. You can see the outdoor temperature reset tank target was 110 degrees. And with indoor temperature feedback, the zones have communicated that their actual temperature needs are only a supply temperature of 90 degrees. So we were able to lower that entering load water temperature from 110 degrees Fahrenheit to 90 degrees Fahrenheit. And let's take a look at what that means for heat pump efficiency. So taking an entering source water temperature of 30 degrees, if we have an entering load water temperature of 90, you can see that my coefficient of performance would be maybe 3.8. And if that entering load water temperature is raised to 110 degrees Fahrenheit, you can see that my coefficient of performance is decreasing to about 2.8. So my coefficient of performance is decreasing by a factor of 1. So I'm losing a lot of efficiency by operating my system with a tank target of 110, when actually what my zones needed in that case was 90. So if I'm able to reduce that tank target temperature whenever possible, using the combination of outdoor temperature reset with indoor temperature feedback, I'm able to get added efficiency out of my heat pump. I will also see fewer distribution losses, and I will have a more comfortable system that doesn't have the same temperature swings, those overshoots and undershoots that you see when we're working with supply temperatures that are higher than they need to be. will also have less heat pump cycling, less expansion noises, so there are a lot of benefits to be had when you operate with the lowest supply water temperatures as possible. And of course the biggest one is that added heat pump efficiency in the case of a geothermal system design. Now we talked about short cycling the heat pump. We know that that has an impact on efficiency. If we are turning that heat pump on and off unnecessarily, we are going to be impacting the COP or the efficiency of the heat pump. Now we can reduce short cycling by installing a correctly sized buffer tank. We can also do it by synchronizing the zone loads, and this is where the control feature zone synchronization comes into play. So new builds are typically designed with distinct zones because separate living spaces in the building have very different heating and cooling needs depending on the location in the building, whether or not they have a lot of window space, etc. In this example, we have a bathroom zone, a living room zone, a bedroom zone, and a kitchen zone. And all of these zones are going to have different heating needs. Now, what happens if we don't try to synchronize and organize the behavior of our zones? So here's the effect of traditional zoning. You can see we have our 4 zones: the living room, the kitchen, the bedroom, and the bathroom. And in blue, we have noted the thermostat on time. So this would be when the heat relay on the thermostat closes and the zone valve opens to allow heat into the space. So you can see they have very different on times. We're not organizing when those thermostats turn on or off. And what effect that has on the heat pump is shown below in red. So the heat pump is turning on here to meet the demand of these zones, and then it's turning off, and then another zone will call, so it will turn back on, turn off, turn back on, and you can see we are cycling that heat pump on and off repeatedly. So our heat pump can have the best onboard control, but if we are not organizing the behavior of our thermostats, then the heat pump is really at the mercy of the zones. The thermostats run the show. What impact does that have on the customer? Well, we have excessive cycling of our heat pump. Our heat pump is turning on and off, on and off. It's not good for the equipment itself. It's going to have a negative impact on the efficiency of the heat pump, so we're going to see higher electric bills than we should, and that's going to lead to unhappy customers. The solution is zoning with communication. So we offer the same zoning solution you're used to. Thermostats connected to a zone box with an end switch. But the difference is that we synchronize our calls. Now, what impact is that going to have? Well, the effect of zone synchronization is that we are going to coordinate the zone on times. So again, here are my 4 zones. Notice they're all going to call at the same time. They're going to start their heat cycles at the same time. Now, as each zone becomes satisfied, they're going to turn off. So the bathroom turns off, bedroom turns off next, and the kitchen. The living room obviously has the greatest demand, so it's staying on for the entire cycle. Only when the cycle is complete can the zones call again. So all the zones are going to call for heat at the same time again, and likewise they're going to turn off as they become satisfied. The impact that has on the heat pump, you can see the on times are longer and there's no repeated on-off cycling. So we're going to have reduced cycles, longer equipment life, and the big one here is the higher operating efficiency. To summarize this 3rd module of our Advanced Heat Pump Control training course, we looked at the components of a ground source heat pump system. So we had the geo side, the heat pump and equipment side, and the distribution side, and how the control solution that we choose can have a huge impact on our heat pump and on our distribution. We looked at the geothermal system design. In particular, we looked at the loop design and sizing. the heat pump selection, and the buffer tank sizing, and why each of those is extremely important to the overall capacity and efficiency of our heat pump system. Lastly, we took a look at the control and the distribution design. So we looked at what are our distribution system options? What kind of terminals can we choose that operate well with the low supply water temperatures? And remember, it's important to have those low supply water temperatures or low entering load water temperatures, because those are what are going to give us the highest possible efficiency in our heat pump. We looked at the control features of outdoor temperature reset and indoor temperature feedback, and how those two control features can be used to lower the entering load water temperature whenever possible. And the lower temperature we have, the higher efficiency we have. So it's in our best interests to try to lower that ELWT whenever we can, and those two features allow us to do that. We then looked at zone synchronization, and zone synchronization is a benefit of having a control solution that includes communication, and that will allow us to have a longer equipment life, to have added efficiency, and to reduce the cycling of our heat pump on and off. So instead of having thermostats run the show, we operate as a cohesive system. And that is something that only the right control strategy is going to provide you. So our third module has come to a close here. Thank you very much for joining me for this third module in our Advanced Heat Pump Control Training for Radiant Heating and Cooling course hosted by HeatSpring. If you have any additional questions about the material that I covered in this course, or if there is something you wish I had covered but didn't in the detail that you wanted or didn't touch on at all, please feel free to send me a message and I'll get back to you as soon as I can, typically within the same day. If not that day, then for sure the following day. And I'm happy to provide additional guidance or answer any questions you have in a more personalized format. I really enjoy getting the feedback from the students, and that feedback is also helping us to further improve our course offerings at Techmar. So thank you in advance for your participation. You'll be hearing from me again soon when we start Module 4. And in that module, we're going to be looking at some particular details when it comes to designing your heating and cooling distribution system, in particular when we're talking about radiant heating and cooling. So I look forward to talking to you all again in Module 4. Thanks a lot. Bye-bye.